Today we're talking about day number 5. We're talking about similar polygons again, but we're going a step farther because we're going to be comparing more than just corresponding sides. If I were to recap what we did yesterday real quickly, I want to highlight this item here. So this was in yesterday's notes. What we're doing is we're setting up these proportions so that we can solve for missing parts of the similar figures. For example, here we had some sides and we had some medians, and we were emphasizing the fact that you can set up these ratios of corresponding parts. They don't only have to be the sides. They could be corresponding heights, what we call altitudes, corresponding altitudes. They could be corresponding medians. That's what we did in this particular example from yesterday, where we were solving for a median, because this median corresponds with this median, just like this side corresponds with this side, and that will happen if they are similar. So we're going to use a dilation in this particular example just so we can get some points on there and some side lengths to work with. But what we're doing is we're going a step farther, because in addition to looking at corresponding sides, in addition to looking at corresponding heights or corresponding medians of triangles, we could even take a look at corresponding perimeters, which is really all of the sides added together at once. So in other words, we're looking at all of the sides at the same time instead of just a pair of sides one at a time. So we're going to work through that and just kind of prove it with a coordinate proof so you can see that it happens. So this looks like a mess. You're like, what in the world is going on? Well, notice you're taking the top side and you're adding it to the right side, and you're adding it to the bottom side, and you're adding it to the left side. So if you've added up all the sides, what do you have? You have the perimeter. So remember, when we are giving you a similarity statement like this, we're saying KLMN is similar to PQRS. Whatever is listed first, that shape's information always goes on the top, and whatever's listed second, that shape's information always goes on the bottom. And because we're adding up all four sides, what we're really doing is we're comparing the perimeter of the first shape to the perimeter of the second shape. And because we're setting it up as this fraction, that's a ratio, so we're going to compare the corresponding perimeters. And this is the abstract concept, and we'll get to the numbers here to explain it here. But what we're saying is that if you compare this perimeter to this perimeter, you'll get the exact same result as if you had just compared the top side to the top side. All right, so if you think about this, what that means is here's a proportion you can now cross multiply for a missing perimeter or a missing side, and so on. But you don't have to use the top side. You could have used the right-hand side. So here you have the ratio of the right-hand sides. You don't have to use the right sides. You could have used the ratio of the bottom side. So here's the bottom sides. Let's see, NM and SR. You don't have to use the bottom sides. You could have chosen the left sides. So we're listing literally every possible option you have, and that's why it looks like such a mess. But what's really happening here is you're setting up a ratio of your perimeters, and then you're just picking maybe one of these ratios of sides. Here, this happens to be the left side ratio, and that's your proportion, and then you can cross multiply. Or maybe you pick not the left side, but maybe you pick the bottom side like this. Here's a ratio on the left equals to the ratio on the right, and then you can cross multiply this way. Or maybe you choose to pick the ratio of the perimeters and the ratio of the right sides, and then you can cross multiply. So again, it looks like a mess because it's all up front with all the possibilities at once, but this is what we're saying. If two polygons are similar, then the ratio of their perimeters is equal to the ratio of the corresponding side lengths, and we're going to prove that now with a coordinate proof. So this is just to get us started here. I went ahead and plotted the pre-image. This is figure KLMN, and so you might want to pause the video here for a moment and just take a moment and label the scale. I'm going up by ones, but we have some pretty big numbers here. And just plot KLMN, and then we'll continue. In this particular case, we want to dilate the figure with a scale factor of 1/2. So remember, a scale factor is a multiplier. So we're going to multiply 1/2 times every single coordinate value. So we want 1/2 of 2. We want 1/2 of 4. We want 1/2 of 2. We want 1/2 of 10. We want half of 10. We want half of 16. We want half of 10. We want half of 4. That's kind of what we're doing in our head, but that's what this is saying. K is your scale factor, and x is being multiplied to your scale factor. K is being multiplied to your y coordinate as well. So half of 2 is 1, half of 4 is 2, half of 2 is 1, half of 10 is 5. Then we have 5 comma 8, and lastly 5 comma 2. So instead of calling it K prime, L prime, M prime, and N prime, we're just giving it new names of P, Q, R, S. But this will be the image after we've shrunk it down. So P is at 1 comma 2. Q is at 1 comma 5. R is at 5 comma 8. And S is at 5 comma 2. So we've already done dilations before. We understand these will produce similar figures. And we've already looked at the corresponding side lengths of dilations, and so we know there will be a consistent, a common ratio and a scale factor with that. But if we were to analyze the corresponding angles, you could see that angle P and angle K are right angles, angle S and angle N are right angles. We don't really know the size of angle R and angle M, but if we were to look at those sizes through tracing paper, we would say those are corresponding parts and congruent. So we've already studied this before. We know that in a dilation, those corresponding angles are congruent. So we just kind of quickly talked about it. We didn't really verify it, but yes, corresponding angles are congruent. That's the first test. And then we're going to compare the corresponding side lengths, but to do that, we need some information on the sides. And so let's count the height of KL. So that is a length of 6. I'm going to jump down here to MN. MN is this one here. That's going to be a height of, or a length of 12. KN is the bottom. That's going to be an 8. And you'll notice I skipped over LM. That's the slanted side, so of course we can't count that. We have to use our distance formula. So just kind of pointing out here that we would set this up with a distance formula. I have 10 minus 2 quantity squared plus sign 16 minus 10 quantity squared. And I'm going to jump to the answer just to fit it in this space here. It actually turns out to be exactly 10. Okay. So then if we were to count the length of PQ, that is going to be a length of 1, 2, 3. You'll notice that is exactly half the size. So we'll check that ratio in a moment down here. The length of RS, 1, 2, 3, 4, 5, 6. The length of PS, 1, 2, 3, 4. And again, QR is slanted, so we have to set up our distance formula on that. And it'll look like this. We have 5 minus 1 quantity squared and 8 minus 5 quantity squared. So jumping ahead to the answer, that will give us a result of 5. So if we compare the ratios of each pair of corresponding sides, we should expect to find a common ratio. So PQ and KL, that's this top line here, but specifically PQ is the left-hand side and KL is the left-hand side. So we're comparing the left sides here. QR and LM, those are the top angled sides. RS and MN, that's the right sides. And then here's the bottom sides. So let's compare each of those ratios. Remember with your ratio, here we have PQ. PQ is on the image, and so we had always said when you set up your scale factor, it's always image over pre-image. So that's why the PQ is on top there. So PQ is a length of 3, KL is a length of 6. You get a reduced ratio of 1/2. And that makes sense because that was our dilation scale factor. Here we have a length of 5 over 10. That's 1/2. Here we have 6 over 12. That's also 1/2. And then lastly 4 over 8. And that's your common ratio, right? 1/2, 1/2, 1/2, and 1/2. Everything up to this point we've talked about before, right? Day 2 is when we were looking at our dilations and showing that those corresponding sides are proportional. Finally, we get to the new topic. And so we had to do all of that background work so that we could now analyze the perimeters, right? So remember, when you add up all 4 sides, that's the way of communicating the perimeter here. So we're saying take the perimeter of the image and the perimeter of the pre-image. All right, so let's see what those numbers are. So PQ is 3, QR is 5, RS is 6, and lastly SP is 4. All right, so we're going to add up all of those, and that means we have a perimeter of 18. Right? So if you walk around that shape, you have a total of 18 units in length. And then on the bottom shape here, KL is 6 and 10 and 12 and 8. So you add up those 4 sides. That is a perimeter of 36. So we're comparing the ratio of the perimeters, and 18 over 36 is 1/2. Look at that. That's the whole point of what we're saying. So when we have similar figures, you can compare corresponding sides. You can compare corresponding heights, corresponding medians in a triangle. That's what we did yesterday. Or corresponding perimeters, which is essentially all the sides added up of each shape. So that's our conclusion. This is the big idea. If 2 polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. And so what we're saying is you could set up this ratio of perimeters equal to this ratio of corresponding left sides. Or you can set up this ratio of perimeters equal to this ratio of top sides. And so on down the line. Because as you can see, they would all equal each other because they all equal 1/2. So let's look at an example where we can make this happen. All right, so here's example 1. All right, we have similar triangles. Triangle PQR, there it is, triangle PQR is similar to triangle WXY. There it is. All right. And in this first triangle, PQR, we actually have all 3 sides provided. So we can add those up and get a total perimeter. So if I were to add up all 3 sides, 72 plus 63 plus 81, that gives me a total perimeter of 216. We don't know the perimeter of this smaller triangle, and that's what we want to find out. So what we just learned is that you can find the ratio of the perimeter. So the perimeter of triangle PQR goes on the top because PQR is first. So this one goes on the top. This one is listed second, so this one will go on the bottom of your ratio. This is the perimeter then of triangle WXY. And we're going to set that equal to the ratio of corresponding sides. And while we have lots of sides on the triangle PQR, we only have one side provided on triangle WXY. So we're going to use the one side that they're giving us. That means it'll correspond with this side here. Now, if you're not sure, because they rotate the objects, remember the order of the letters will tell you this. So this is side WX. I got to use that side. That's the first and second letter of that triangle's name. So that'll pair up with the first and second letter of this triangle's name, which is segment PQ. And yeah, PQ is on that left-hand side. So I'm not plugging in the numbers just yet. I'm just showing you the concept. What we're looking at here is the ratio of left sides. It's the ratio of corresponding sides. So I'm just going to make a note of that. This is your ratio of corresponding sides, or left sides to be specific, right? And then here I already have labeled this is the ratio of your perimeters. So if we plug in the information, perimeter of triangle PQR is the 216. The perimeter of triangle WXY, I don't know. That's our variable. So call it an X. I'm not going to call it a P because we have a point P. I don't want to confuse that with perimeter P's. We do have an X, but that would be a capital X, and this is like a little lowercase x. Pick whatever variable you want. PQ is a length of 72, and WX is a length of 40. So there's your proportion, and now we can cross multiply. So here we have 72 times x. Here we have 40 times 216, which gives us 8,640. And then, of course, we're going to isolate the variable by dividing both sides by 72. So that gives us a result of 120. Now, again, that x is representing the perimeter, and so we know that these three sides have to add up to 120. So notice that's kind of clever. We can find the perimeter even though we don't know all of the sides to add up. But if you did add them up, they would have to add up to 120. So let's do that again with this next example to the right. We're still looking at the ratio of perimeters. And this time, instead of giving us two sides to set up the ratio of sides, what they're giving us instead is just the scale factor. Assume the scale factor between triangle PQR and WXY is 3 to 4. All right, so what that means is PQR is listed first, so it gets the 3. WXY is listed second, it gets the second number of 4. So PQR gets the 3. All right, now we don't know what side it belongs on, but that doesn't really matter because what we're doing is we're essentially taking the sides and reducing them down, so it's a ratio of 3 to 4. So for every 3 units of length on this triangle PQR, there's a corresponding 4 units of length on this triangle WXY. So the reason I'm putting the 3 here and the 4 here is these happen to be corresponding sides. How do I know that? Because again, I'm looking at the order of the letters. P and Q are the first and second letter, so I'm talking about this side here. And if I pair that up with the first and second letter, and this triangle's name, WX, is over here. But I could have put the 3 on any of the sides, and I could have put the 4 on any of the sides. So again, we do have a perimeter of triangle PQR. That's this one here. So this perimeter is a total of 84 units, and this perimeter we don't know. But we do know it has to be larger, because if you compare the scale factor, 3 is smaller, 4 is bigger. That means this perimeter has to be bigger than 84. So once again, I'm going to set up a little labeling here of a proportion, and then we'll plug in the numbers. So I'll try to squeeze it in right here. So this is the perimeter, I'll abbreviate it like that, PER. This is the perimeter of, I'm going to list this one first, triangle PQR over the perimeter of triangle WXY. And that will equal, now in the previous example, we had the ratio of corresponding sides because we had specific side lengths. We technically don't have side lengths, but we have the reduced ratio of side lengths, which is the scale factor of 3 to 4. So 3 to 4. So now the perimeter of triangle PQR is 84. This perimeter I don't know. I'll give that a variable, and that equals 3 to 4. And now we're going to cross multiply. So you have 3 times x. You have 84 times 4, which gives us 336. Divide both sides by 3 to isolate the variable, and we end up with 112. So that is the unknown perimeter. So once again, notice we can solve for the total even though we don't know the individual lengths. We don't have the 3 sides to add up. We're just scaling up the given perimeter using the scale factor like this. I'm skipping example 2 because that's not quite what we're focusing on. We're focusing really on just the ratio of the perimeters here. And that will be enough for our examples today.